Hi everyone. Let's talk about L'Hopital's rule. We are given two limits. We must compute them by using any method we wish. If you would like to try this exercise on your own first, stop the video now. You can download these notes using the link in the video description. The first limit is a limit at infinity. If you don't know how to compute limits at infinity, in the video description you can find a link to a video in which I explain limits at infinity in detail. As x goes to infinity, the numerator goes to infinity, and the denominator also goes to infinity. This limit is of the form infinity divided by infinity. To deal with it, I will use a method of leading terms. The leading term in the numerator is x. The leading term in the denominator is x squared. This means that this limit is the limit as x goes to infinity of x divided by x squared. This expression simplifies to 1 over x. And as x goes to infinity, the denominator goes to infinity, which means that the entire fraction gets closer and closer to 0. This limit is 0. The second limit is of the form 0 divided by 0. If you plug in 0 to the denominator, you get 0. If you plug in 0 to the numerator, you get sine of 0, which is 0. This limit is of the form 0 divided by 0. We know some techniques to deal with limits of the form 0 divided by 0. The techniques are multiply by the conjugate, factor, simplify a complex expression. Unfortunately, none of those techniques would work here, which shows a need for a new method. This new method is called L'Hopital's rule. L'Hopital's rule says that if we are given two functions, f and g, both of them differentiable, and there is some technical requirement that the derivative of g is not 0 near a, and if we want to compute the limit of f of x divided by g of x, and that limit is of the form 0 divided by 0 or plus or minus infinity divided by plus or minus infinity, then to compute the limit, I can instead compute a different limit. A limit, as x goes to a, of f prime of x divided by g prime of x. Today we will focus on using this rule. In a different video, I will show you why this rule is true. In the next problem, we must use L'Hopital's rule to compute the two limits from the first exercise. According to L'Hopital's rule, if the limit is of the form infinity divided by infinity or 0 divided by 0, you can apply L'Hopital's rule. The first limit is of the form infinity divided by infinity, which means we can apply L'Hopital's rule. To denote that I'm using L'Hopital's rule, above the equal sign, I will write infinity divided by infinity to remind myself that this is the form of the limit, and at the bottom, I have to tell the reader that I am using L'Hopital's rule. I will do it by putting the letters LH next to it. So I'm using L'Hopital's rule now. And I will get the limit as x goes to infinity. And according to L'Hopital's rule, instead of looking at this limit, I look at the limit of the derivative divided by the derivative. The derivative of x plus 1 is simply 1. The derivative of x squared plus 3 is 2x. What happens to this limit as x goes to infinity? Well, the denominator gets larger, so the whole thing gets smaller and smaller. This limit is 0, and we obtain exactly same answer as in the first exercise today. The second limit we claimed was of the form 0 divided by 0. L'Hopital's rule says that if you have a limit of the form 0 divided by 0, you can instead compute the limit of the derivatives. Let me do that. Instead, I will apply L'Hopital's rule now, and I will take the limit as x goes to 0 of the derivative of sine is cosine, the derivative of x is 1. What will happen if I plug in 0 to this expression? In the numerator, I will get cosine of 0, which is 1. In the denominator, I get 1. So this limit is 1. Let's see if we can apply L'Hopital's rule to a few more limits. If you would like to try the next problem on your own, stop the video now. In part A, we are given a limit as x goes to 1 of ln of x divided by 1 minus x. If I simply try to plug in 1 to this expression, in the numerator I would get ln of 1, which is 0. In the denominator I would get 1 minus 1, which is 0. This means that this limit is of the form 0 divided by 0, a required form for L'Hopital's rule. This allows me to use my rule, and I get the limit as x goes to 1 of, and now I take derivatives of the numerator and of the denominator. The derivative of ln of x is 1 over x. The derivative of 1 minus x, the derivative of 1 is 0, the derivative of negative x is negative 1. Well, this is the same thing as the limit as x goes to 1 of negative 1 over x. As x goes to 1, this expression gets closer and closer to negative 1 divided by 1, which is simply negative 1. In part B, we are given a limit as x goes to infinity. As x goes to infinity, 1 over x gets closer and closer to 0, which means e to that power gets closer and closer to 1. This means that in the numerator I have 1 minus 1, which gives me 0. In the denominator, as x goes to infinity, 1 over x goes to 0 as well. So this is of the form 0 divided by 0. Because it is of the form 0 divided by 0, I can use L'Hopital's rule. And I get the limit as x goes to infinity of, and now I take derivatives. Let me start with the denominator. The derivative of 1 over x is negative 1 over x squared. And that is because 1 over x is the same thing as x to the negative first power. When you move negative 1 down, you will get negative 1x to the negative second power, which is negative 1 over x squared. In the numerator, I have the chain rule here. The derivative of 1 over x is negative 1 over x squared. I multiply it by the derivative of the outside function with the inside function plugged in. So I multiply it by e to the power 1 over x. The derivative of negative 1 is 0. I don't write it down. Now I see that a few things cancel. Negative 1 over x squared in the numerator cancels with negative 1 over x squared in the denominator. And I get the limit as x goes to infinity of simply e to the power 1 over x. We know that 1 over x gets closer and closer to 0, which means e to the 0th power gives you 1. This limit is 1. Let's try part C. We have the limit as x goes to 0 of this expression. If I was going to plug in 0, I will get sine of 0, that's 0, minus 0, that gives me 0 in the numerator. In the denominator, I also get 0. This is of the form 0 divided by 0. I'm going to apply L'Hopital's rule. That gives me the limit as x goes to 0 of, I take the derivative of the numerator, the derivative of sine is cosine, the derivative of x is 1, so I have minus in between, negative 1. In the denominator, I get 2x. What happens if I plug in 0 now? Cosine of 0 is 1. In the numerator, I get 1 minus 1, that gives me 0. In the denominator, I get 0. This is of the form 0 divided by 0. Well, let me apply L'Hopital's rule again. When I do that, I get limit as x goes to 0 of negative sine of x divided by 2. Plugging in 0 to this expression, sine of 0 is 0, gives me negative 0 divided by 2, which is simply 0. In the last example, I have a limit as x goes to 1 of this expression. When I plug in 1, I get 1 squared plus 5 divided by 3 times 1 plus 4, which gives me 6 divided by 7. I did not apply L'Hopital's rule here because the limit was not of the form 0 divided by 0 or infinity divided by infinity. I could simply compute it by plugging the number in. What would have happened if I took the derivatives? Will I get the right answer? Let's try. If I compute the limit of the derivatives, the limit as x goes to 1 of the derivative of the numerator and the derivative of the denominator, will I get the right answer here? The derivative of x squared plus 5 is 2x. The derivative of 3x plus 4 is 3. Plugging in 1 to this expression gives me 2 divided by 3. This is wrong. These two numbers are not the same. This means that when you compute limits, you have to be very careful. You can only use L'Hopital's rule if the limit is of the form 0 divided by 0, or infinity divided by infinity, or negative infinity divided by negative infinity, or infinities with any signs, kind of like we had it here. Otherwise, you are not allowed to use L'Hopital's rule.